Hello. In this video, I'm going to show you how to implement the local average treatment effect using the example from Angrist and Evans 1998 paper. This paper is about the number of kids on mother's labor supply. And I think this is the last online video on implementation of the methods. Okay. So let's review the local average treatment effect model. So we are basically the idea motivation of the local average treatment effect model is that we cannot randomize the treatment. For example, in our example, the treatment is number of kids. We cannot randomize, And then instead of randomizing D directly, we consider an alternative randomized variable like the instrument. As you know, in our example, twins, for example, and the sex composition of the first two kids are randomized variable. Like we do not randomize, but we can comfortably assume that like having twins is a random event, right? And to accommodate this randomization of Z, the instrument, we are going to extend our potential outcome framework such that the treatment decision D also depends on the instrument. So there are already potential treatment decisions. So if you are assigned a certain value of Z, then your treatment decision will dependent on that. So that means your number of kids will depend on whether you have twins or not, or whether you have a boy or girl in the first child or not, something like that, right? So depending on the realization, you will make further decision on the number of kids. And then, because we defined potential treatment decision this way, we could think of 4 different types of people. Like you may remember, always takers, never takers, compliers, and defiers. So always taker, never takers are like intuitive what they mean, right? Compliers are those who follow what is given, like given by the randomization of Z. But defiers are those who do not follow, right? Go the opposite way. So you may remember that these 4 groups are defined by binary treatment decision depending on binary instrument. So 2 by 2, 4 groups. And then furthermore, then the potential outcome Y has to depend on not only on the treatment decision, but also conceptually, we have to allow the dependence on the instrument because that's how we consider the timeline. So instrument realizes first, and then treatment, and then outcome. So that's given this timeline, we have to think about potential outcome depending on 2 previously realized variables. And then on this generalized extended potential outcome framework, we are going to make 4 assumptions. So in the end here, in the first assumption, we are going to remove the dependence on Z. The potential outcome does not depend on Z. That is our assumption. So the effect of Z is only through the treatment D, right? So that is the first assumption. Z, the instrument, has no direct effect on the outcome. By the way, remember, this is the same assumption as we made for the instrument, right? Z is instrument, so we are doing the same thing. And second assumption is that the instrument should be independent of all the possible potential outcomes, potential decisions, potential outcomes. So randomization assumption. So Z should be perfectly random. And third assumption is that the probability of treatment must be different across instrument those who receive instrument equal to 1 or 0. Right, so depending on the value of instrument, the probability of treatment should be different, which is natural. So you are designing the instrument so that it affects your choice. So if they are the same thing, if these two probabilities are the same, that means the instrument has no effect on the treatment choice. So your experiment is useless, right? Does not change the treatment. And finally, the assumption number 4 is the most interesting and important assumption, that there are no defiers. Defiers are not allowed, and I have explained this assumption is to accommodate heterogeneous treatment effects. Different groups of people can have different treatment effects, and then defiers cause some problem. The estimator can be biased if there are defiers. Okay. Now, under those assumptions and under the extended potential outcome framework, we could show that the average treatment effect given compliers, so average treatment effect for the compliers, which is the local average treatment effect, equals the right hand side. It depends on observed variable y, z, and d. So this is called the Wald estimator in the textbook. So what it means is, so we can calculate the right hand side. The right hand side is a Wald estimator. We can calculate that. I'm going to show you how to calculate that. It's pretty simple. And under those assumptions, we know that this equals to the average treatment effect for someone. That's compliers. For the compliers, so we could identify something. And remember, this is only for compliers because we could not randomize the treatment directly. Instead, we have indirect randomization through Z. So I explained this this way. So the compliers are the only group who are affected by the randomization of the instrument. That's the only randomization power we have. So randomization of the instrument can identify only this group. Everyone else, like always takers, never takers, are not affected by the randomization. Then we cannot do anything for them. So we only identify the compliers. Okay. So then let's go back to our real data. So by the way, the data we use are the same as what we do in homework 5. By the way, I include a few more variables that are not used in our homework. Basically, the same data we use in the textbook, in the class. So the dependent variable, the outcome variable y, can be either the mother's employment, which is binary. If the mother is working, then it equals 1, otherwise 0. And hours worked per week. So you can also think about hours worked. And the treatment is whether a woman has 2 kids or more than 2 kids. So it only includes a woman with at least 2 kids. Right? One woman with only 1 kid is not included in our data. And all the observations having more than 2 kids are just considered as treatment, right? Even like 3 kids, 4 kids, 5 kids are all just treated. So we would like to estimate the effect of having more than 2 kids relative to having exactly 2 kids. All right. And then, interestingly, there are 2 instruments. One was twins. So Z1 is 1 if it happened to be twins or multiple births at the second birth. So you like at the second birth, if you have twins, then automatically you have the third kid or more. So this is if you believe and having twins is random. So this randomization changes your number of kids. So it's an interesting and very valid instrument. And the other instrument we consider is the sex composition. Like Z2 equals to 1 if the first two kids have the same sex, right? If you're like for example, if you wanted to have a girl and if you happen to have two boys, then you are more likely to have the third kid. That's the idea behind this instrument, right? So it is also like and interesting to see how they work in our analysis. So the data are also from 1980 census data, and it was used Angrist and Evans, and this example has been used 3 times in the textbook. Table 3.4.2. This is your homework, right? In this case, you had to consider, Probit model, Tobin model, right? Table 4.1.4 and table 4.4.3. These are based on the local average treatment effects. So we are going to replicate them. So implementation is actually pretty simple because first, Wald estimator is simple. And then I'm going to show you actually the Wald estimator is equivalent to the IV regression, two-stage least squares regression model. And then we will additionally analyze how to handle multiple IVs at the same time, and we will study how big the complier group is. So I'm going to play with the data, right? So by the way, what I wanted to tell you first is that Stata is not optimal to implement Wald estimator. Like to see that, let me start with Excel. Actually, Excel is more convenient to implement the Wald estimator. The Wald estimator is the right hand side, this guy. So basically, it's pretty simple. What we are going to do is we are going to calculate expectation average of D for those who have twins and for those who do not have twins, and take difference, and do the same thing for the outcome and take the difference, and then take their ratio. So each step is pretty simple, right? But it's not easy. I'm going to do that. It's possible, but not easy on Stata. So back here. So let me explain the data a little bit first. So maybe having 200% will help you to see what's going on. So kid count, it's same data as homework 5, so I'm going to skip a few variables, but here these variables may not exist in your homework. So boy variables, and multiple birth at the second birth. So twins, this is an indicator for twins, and same-sex variable, whether the first two kids have the same sex or not, right? So these are the variables we are going to use as the instrument. So these are the instruments, and this variable more kids equals 1 if the number of kids is greater than 2, right? 1 if the number of kids is greater than 2. So this is our treatment. Our treatment is more kids, and our outcome is either hours worked, mother's hours worked, or where is that? Like this one, employment, whether mother is working or not, right? So let's see. First, I'm going to consider like hours worked and twins instrument case. We can think about this case, and later we are going to consider like worked M and twins, and then we can also think about hours M and same sex, and worked M and same sex. So we can, depending on which outcome we use and which instrument we use, we can think about 4 different cases. Let's do this. First thing we are going to do is we are going to calculate. We are going to calculate these 4 things first. that is each component of the Wald estimator. And how do we do that? Like, we can use average if command, like a formula, or you may use average if formula here, and using that z equals to 1 twins sex variable, like so we have sex variable equals to 1, and average is, we are going to take the average of worked hours, which is here. Okay. Then we have 16.43. So if more than 2 kids, excuse me, if mother had twins at the second birth, the average working hours was 16.4. We can do the same thing for the other guys. We can just copy it. We will copy that and put it here. But the difference is we change the condition to 0, right? So we are calculating average for those who do not have twins, right? And then we will get this result. And now we are going to calculate the average for the treatment, average of the treatment for those who have twins. Then you will find 40%. 40%. Excuse me. Let me see. Right. Oh, I'm sorry. So this is not for twins. This is same sex. So it's my mistake. I'm sorry. I used this column, not this column. I had to use column P, but I used column Q. Anyhow, we were going to do that. And finally, we calculate average. So we used average if formula on Excel to calculate the conditional expectation. Literally, average if is the conditional expectation, right? And then, as you can see, if the first 2 kids have the same sex, the probability increased from the probability of having the third or more kids increased from 33% to 40%. So that is the effect of instrument. And Wald estimator will look like this. So remember, we take the difference in the conditional expectation outcomes and the difference in the treatment. Then you are going to get something given this way. Okay, so this is same sex and hours thing. And the Wald estimator tells you that the effect of effect of the third kid is -5 hours per week. Like if you had a third or more kids, then the mother is likely to work 5 hours less per week. Okay, so now then let's do hours and twins. Basically, we are going to copy these guys. Like there's a slight change. Excuse me. So let's do it again. So average if, we are going to calculate the average if range. The condition range is using the twins. So we have what? Right. I should have not entered it. So and its condition is 1. If twins area equals to 1, then we calculate average of hours. This is the average hours for those who have twins. So this average is of course different because I changed the variable. And let me simply just, copy this for simple computation. Now in the second row, I change 1 to 0. Now then this is the average of working hours for those who don't have twins. And this cell, I'm going to change the outcome hours, like we are calculating average of more kids. So delete this, and here we will put the treatment. And similarly, we are going to copy this and put here and change the condition from 1 to 0. So what is interesting now here is if you have twins at the second birth, then you are going to have a third kid for sure. So this probability is 100%. If you have twins, then the probability of having the third kid is 100%. So I've actually, when I tried this before recording this video, I thought it was an error, but it is not an error. Literally in our data, there is no family, which is natural and good. No family who have only 2 kids when they have twins at the second birth. So if you, if like one of the baby died or something like that, then that could be the case where this is not 100%, but we don't have that case in our data. But still, if you do not have twins, then only 36% had the third kid, right? Now let's calculate the same Wald estimator in the same way, like by taking difference between these two guys, taking difference between these two, and divide by them. Then you will get minus 3 hours. So this effect and this effect are different. So the idea is, because you are using different instruments, then you are identifying different complier groups. So your result will be different. This is not surprising, right? Now we are going. You can do the same thing for work like employment, right? Average if. Let me go quickly. Average if multi-second. Excuse me. No. So if your same-sex instrument is 1, then we are going to calculate the employment. Where is employment variable? Calculate the average of employment variable. Then you are going to get 52%. So 52% of women, mothers, work if they have the same sex for the first 2 kids, right? And you are going to get similar, like, let's see. If you do not have the same sex for the first 2 kids, the employment rate increases to 53%, right? So in strange, like the sex composition affects employment rate. That's because it affects the number of kids. Now we are going to calculate not the average of employment, but the average of more than 2 kids, more kids. So treatment. And then what you see here is if you have same sex for the first 2 kids, your probability of having more than 2 kids is 40%, 40.67%. But if you had different 1 girl and 1 boy for the first 2 kids, you are going to have only about 34%. The same numbers, of course, they are the same numbers, right? And then Wald estimator is minus 12%. So using the sex composition, we can find that if you have third kid, then the mother's employment rate will drop by 12 percent point. So that is Wald estimator. And let me erase these things. And then we can do, you will see the same, like the same pattern going on here. If you think about twins, like actually I can copy this. This part is the same as the second column. Now we only need to change this part from same sex to twins. So our condition becomes twins. So if you had twins, if a mother has twins at the second birth, the employment rate is only 47%, nearly 48%. And compare that to those who do not have twins. Then if you don't have twins, it's 52%. Calculate the ratio. Wald estimator is only 7.6%. So earlier, if you use the other instrument, same-sex instrument, the estimated effect of the third kid was 12 percent point, but with twins instrument, it becomes 7.6%, right? So this is what we can do, how we can implement Wald estimator on Excel. So there was no special technique, but using average if formula. But I believe it's not new, not drastically surprising to you. But now let me explain why this is not easy on Stata. Because on Excel, we made this is a kind of extra space, right? On Excel, you can easily just extend spaces and write down whatever you want. But on Stata, there's nothing like that. Okay, by the way, let me open the data, change directory, and open data. Not this one. This one. So in this data, we want you to calculate conditional mean. So like for example, you can calculate the conditional mean like this: more kids over same sex. So this is how we calculate the conditional mean. You could calculate that. This is the same number as these guys. These numbers can be calculated on Stata using this command. But it is not saved. You can, what you can do is you can copy this number and go back to Excel and copy the number here and calculate on Excel. Then that's basically the same thing what we did here, right? So Stata, Excel you have more freedom to enter numbers on the side, but Stata does not have that space. It is possible, but it requires a more advanced command. Let me show you how to do that. What we are going to do is egen. Egen is kind of advanced command for generating another variable. So let's just see what I'm doing. So I'm going to define t1 variable. It's kind of generate command. Generate t1 variable, which is defined as mean of more kids. So exactly I'm doing this, and I will divide it by, say, same sex equals to 1. Then let me show you what we have a new variable. What happens is, if you open data editor, data viewer, then we are defining a new variable which is filled with the same number all over the observations. So it is kind of waste of your memory, right? But that's how Stata is designed. If you use another program like R, MATLAB, Python, it'd be more flexible, so you could do it more efficiently. But Stata is not that efficient. You can keep doing the same thing, like for example, oh, what happened? Oh, like I forgot to enter equality. So if you define on the similar mean, like, you know, these numbers are the same numbers as we had here, right? And mean y, say y is ours m. So we can calculate 4 conditional expectations like these, like as 4 new variables. But as you can see, it's really inefficient way. And finally, you may generate Wald estimator as their differences, like y1 minus y0 divided by t1 minus t0. Then that is the Wald estimator. Excuse me. That's the Wald estimator minus 5.22. So also Wald estimator is defined as a new variable, and like more than 20,000 observations have the same values. Inefficient use of memory. But anyhow, in the end, the result is the same. Okay, so the same result to implement Wald estimator. But a better way is using IV regress. Let me use IV 2SLS. I have done this. I have shown you how to do this earlier. So if you use IV regress command, two-stage least square method, same thing. Ours m same sex, ours m more kids same sex. You know, same set of variables. Then you are going to get 5 minus 5.22. Remember, this is the same number as Wald estimator. So what I wanted to show you here is, first, Wald estimator is basically the same as two-stage least squares. In this simple case, there is no control variables, only one instrument. Everything is binary. Then you don't. It's the same. Like, and also IV regress. You may change the outcome. If you use employment as the dependent variable, it is minus 0.12. So 12.7% point decrease is the number we obtained here. So no matter what you use, basically two-stage least squares will do the same thing. And actually, this is better. This is better because it automatically calculates standard errors and all the side variables, side analysis on the side, right? So I wanted to show you Wald estimator is theoretically simple, but simple in theory doesn't mean simple in implementation. In practice, regression is mostly, in most cases, the better, the more convenient way. And this is not desirable, not ideal. So that's what you can see here. And also, using IV regression is also very useful because we learned we can use more two instruments at the same time. So as you see, IV regress two-stage least squares, ours m, and here you may include 2 instruments at the same time. Then still it runs. It runs, and the final estimate is minus 3.6 hours. So the estimated decrease in working hours for mothers with third kid is minus 3.6. And we learned, in theory, in the class, we learned this number is weighted average of different compliers. So because we are using 2 instruments, you can think about two different compliers, and the regression result is a weighted average of them, right? And the weight can be calculated mathematically, but anyhow, it's some new new estimator using two instruments at the same time. Okay, and what we can do here is, like, we may also include other variables. Like, I will include age at the first birth, and racial dummies, and education dummies, right? And then so look at this command. If it's too small to see that, like IV regress two-stage least squares, and this is the dependent variable, ours m, and this much is control variables. I included control variables, age at the first birth, and like racial dummies and education dummies outside of the parenthesis. And inside the parenthesis, you are like defining the first stage relationship. And then if you run this, you are going to get another slightly different result, where the coefficient of more kids is minus 3.56. Similar, but slightly different. Now you can say that this regression adjusts the control variables, and control variables are calculated this way. Okay, so this is how you, like, in the end, my conclusion is that we learned Wald estimator because it is simple. But in practice, with the data, what you're going to do is two-stage least squares. Like I said, regression is almost always our method of computation. So you are going to use two-stage least squares with instruments. Okay, and in the in the two-stage least squares implementation, we regress in the first stage regression of the two-stage. We regress more kids on same sex, for example. So this was our first stage regression. And remember, more kids on same sex, the coefficient was 6.7%. And by the way, this number is the difference between these two guys, right? So if you calculate the difference, 0.06762, this is this coefficient, which captures the how much probability, how much increase in the treatment when the instrument value changes, right? When the instrument changes from 0 to 1, how much of women will have a third kid? That is the first stage regression. And in other words, this is the percentage of complier group. So you can calculate. So you can say that in this example, you can say that 6.7% of the data of the observations are compliers. I don't know who are compliers, but I know the percentage of them, right? So similarly, you may use twins instrument. If you use twins instrument as a regressor, then the probability is 63.1989%. This, as you can expect, that number is the difference here, right? Difference using twins is 63%. Then we can interpret this coefficient as the probability of percentage of compliers with the twins instrument. So, like, so 63% had to have the third kid because they happen to have twins, right? Then who are the other 36%? They are always takers. They will have third kid no matter, even if they don't have twins, right? So 36% are going to have the third kid even if they don't have twins, but the other 63% are forced to have the third kid by the randomization of twins, right? So that's how we interpret the first stage regression. If you run this, then that's the information from the first stage regression will tell you the percentage of compliers implied by the instrument. So as you can see, twins variable has more compliers because it's more forcible, right? Twins is affecting more directly on the number of kids. Same sex has only 6%. So, and because only 6% of people have strong preference toward their kids' gender composition, right? And then additionally, what I'm going to show you is the percentage of compliers, like say, for example, percentage of compliers among college graduate. How do we do that? We are going to regress more kids on same sex if what I'm going to do is I add this option. So regress more kids on same sex if college graduation dummy equals to 1. So if you are college graduate, do the same thing, then what you find is only 4.7%. 4.7% among college graduates are compliers. In this case, 4.7% have preference toward their kids' sex, right? That's how we can interpret. Let's see what happens among high school graduates. So I changed the condition to high school graduation. Now that percentage is similar to the overall percentage, like 6.7%, which is similar, and it makes sense. So more highly educated people tend to have less preference toward kid sex, less affected by kid sex, so makes sense. You may do the same thing with twins instrument. So among college graduates, the compliers are 71%. There are much more compliers, right? So 71% did not intend to have the third kid, but they had to have the third kid because of twins, right? So 71%. The other 29% are going to have the third kid regardless of twins. So because of the higher education, the intention to have the third kid is lower, and there are more compliers. Let's do the same thing for high school graduates. The compliers are only 65%, nearly 66%. So that means the other 34% intended to have the third kid regardless of twins, right? So that percentage is higher among high school graduates than compared to the percentage among college graduates, which makes sense. So as you can see, this is how we can implement and how we can interpret the local average treatment effect and instruments and the compliers, right? And as you can see, implementation is pretty simple. By the way, now I'm not going to use do-file editor because what I did was pretty simple or pretty inefficient. So in conclusion, in implementation, you are going to use regression, and Stata is optimally designed for regression, not simple calculation like what you do on Excel. So Excel could be still useful in doing this. Okay. Okay, this was the last lecture. Thank you for watching this, and if you graduate this May, I hope you have a good time next week, and also good luck with your final exam, not only in this class but any other classes. And if you need help, let me know. I'd be happy to help you. And thanks for the great semester. Enjoy the summer. Bye.